in section 14.3, we go over partial derivatives. So first, we're going to discuss how to calculate partial derivatives. Looking at a function of two variables, f of x, y, we can define a partial derivative for each variable separately. So a partial derivative for x and a partial derivative for y. So the partial derivative for f with respect to x is written like this, right? So it looks like the notation that we used previously, except because it's a partial derivative, we use this curly d to denote df dx. And the way it's computed is by following the ordinary differentiation rules with respect to the variable x, and while you treat y as a constant. And then similarly, the partial derivative with respect to y is calculated by differentiating with respect to y while treating x as a constant. So this is the notation, and I mean, sometimes, especially when we repeatedly take partial derivatives, instead of using the df dx and df dy notation, we can use the subscript notation. So it's kind of like the prime notation in single variable calculus, except because we have separate variables, we denote the partial derivative with a subscript. So f sub x means the partial with respect to x, and f sub y means the partial with respect to y. Okay, so so again, the way to calculate the partial derivatives is described here. So let's apply this to example 1, where we have this polynomial function f of x, y, 3x squared plus x cubed y plus 4y squared, and we want to determine the two partial derivatives. So let's first take a look at df dx. So to take the partial with respect to x, whenever I have the variable x, I take the derivative normally, and I treat y as a constant, right? So here this term only contains x, so the derivative of 3x squared is 6x. The middle term here contains y, so again, I'm just thinking of y as a constant, so that's like the coefficient for this, and so the derivative of x cubed would be 3x squared. So I get 3x squared, and again, y is treated as a constant, so the derivative doesn't apply to the constant coefficient. And then here, again, I'm treating y as a constant, so this term doesn't contain x at all, so I'm thinking of the entire term as just a constant, and the derivative of a constant is equal to 0, so this term goes away. Okay, so the partial derivative with respect to x is this function here. Okay, so now let's take a look at the partial with respect to y. So going back to the original function, and now I treat x as a constant. So if x is a constant, then this whole thing doesn't depend on y at all, so I'm treating the whole thing as a constant. So derivative constant is 0, so this term goes away. Here the x cubed is thought of as a constant, so this is just like a constant times y, so the derivative is just the coefficient, which is x cubed. And then finally, this term only contains y, so the derivative with respect to y would be 8x, 8y. Okay, so I get this as the partial with respect to y. And then finally, we're asked to plug in some values into each of the partials, right? So here, I'm plugging the point 1, 0 in. So just plugging the x and y values in, to the partial with respect to x, you get 6 times 1 plus 3 times 1 squared times 0. So calculating this is 6 plus 0, which is equal to 6. And then I'm also asked to calculate the partial with respect to y at the point 2 comma negative 1. So just plugging the values in, you get 2 cubed plus 8 times negative 1. So this is 8 minus 8, which is equal to 0. Okay, so this is the first example.